All right, strap yourselves in, because today we're blasting off into the wild world of warp drive. And trust me, this isn't just some sci-fi fantasy. We're talking real science, mind-bending theories, the works.
It's amazing, isn't it? Something that sounds like it's straight out of Star Trek is actually a topic that serious physicists are grappling with. This whole idea of exceeding the speed of light, it's enough to get anyone's imagination going.
Absolutely. And that's what we're here to explore, the nuts and bolts of warp drive. From the mind-boggling math to the paradoxes that still have scientists scratching their heads. Could we actually one day zip across galaxies faster than the speed of light? Let's dive in.
Our journey starts with a physicist named Miguel Alcubierre, who back in 1994 threw a real curveball with something called the Alcubierre metric. You see, instead of trying to make a spaceship go ridiculously fast through space, he proposed warping space itself.
Hold on, warping space itself. Now that sounds like something out of a Christopher Nolan film.
Exactly. Picture space-time as this giant, flexible sheet. What Alcubierre imagined was creating a sort of warp bubble around a spacecraft, contracting the space in front of it and expanding the space behind it. Kind of like a surfer riding a wave.
Okay, so instead of blasting through space, we're talking about manipulating the very fabric of the universe to take a shortcut. That's wild.
Exactly. And here's the really cool part. The spacecraft wouldn't actually be breaking the speed of light locally. It's all about manipulating the geometry of space-time, not exceeding some kind of cosmic speed limit. And at the heart of all this is the idea of York time.
York time? Okay, that one sounds a little intimidating. Break it down for us.
Okay, imagine a river, right? In some spots, the current flows faster, so you get a quicker ride downstream. York time is kind of like that, but for space-time. It describes where space-time is flowing faster or slower, and this warp bubble, in theory, would be able to ride those cosmic currents.
So basically, we're talking about hitching a ride on the universe's own superhighway system. I like it. But hold on a second. Doesn't Alcubierre's idea have a bit of catch? If you're warping space itself, how do you actually steer? It'd be like getting in a car with no steering wheel.
You're absolutely right. That's one of the big head scratchers. How does this warp drive know which direction to go? That's where the concept of a boost field comes in, which was further explored through the development of something called the canonical form of the metric.
Canonical form. Now that sounds complicated.
Don't worry too much about the technical jargon. It's really just a way to write those mathematical equations more elegantly. The important thing is that it highlighted just how crucial this boost field is.
So what is a boost field exactly? Like some kind of turbocharger for our warp bubble?
You got it. It's like a multiplier that amps up the initial velocity of our warp drive. Imagine it as a way to fast forward time within that warp bubble.
Ah, so the boost field is kind of like our steering wheel, giving our warp-capable ship direction. But this boost field, it's not just some simple add-on, is it? Doesn't it lead to some really mind-boggling consequences?
You're right, it does. And one of the most bizarre is something called the pseudo-horizon. Picture this.
Pseudo-horizon, huh? Sounds like we're about to cross into some pretty weird territory, even for this conversation. What's going on there?
Basically, imagine our warp bubble cruising through space-time, and around it, this kind of boundary forms. And at that boundary, photons, those tiny particles of light, they start acting really strangely.
So light itself is getting warped.
Yeah.
Okay, now that's really making my head spin.
Yeah, it's kind of similar to how light bends around a black hole, in the sense that we're talking about really intense gravity warping the fabric of space-time. But with this pseudo-horizon, it's like light is hitting the fast-forward button because of the boost field, causing it to, well, behave in ways we don't fully understand. And, this whole idea of a boost field manipulating higher dimensions, it reminds me of what another group of physicists, Chung and Fries, proposed with something called the Chung-Fries metric. They were tackling this idea of hyperspace, like in science fiction.
Oh, yeah. Like punching it into hyperspace, Star Wars style.
Well, not exactly, but they were onto something. Chung and Fries, they suggested that our universe might be like a slice of bread, right? And this slice is just a tiny part of a much bigger loaf. We're embedded within this higher dimensional space, what physicists often call the bulk.
Hold on. You're saying our entire universe is just this tiny part of something much, much bigger, with more dimensions than we can even wrap our heads around. That's a mind-blowing thought.
It is. And get this, Chung and Fries, they theorized that this boost field we've been talking about, that's the key to unlocking these higher dimensions. So instead of traveling through our normal 3D space, this warp drive would be taking a shortcut through hyperspace.
So it'd be like finding a cosmic wormhole, this secret passageway through the fabric of reality. Okay, now I'm really starting to see why everyone gets so excited about warp drive. This isn't just about building faster spaceships. It's about unlocking the universe's deepest secrets.
Exactly. It's about pushing the boundaries of what we think is possible. But, you know, even if we never quite figure out interstellar travel, this whole warp drive research, it could lead to some incredible advancements closer to home. Think about missions within our own solar system.
Now, that's something I can definitely get behind.
Right. I mean, a trip to Mars that takes months right now could be shortened significantly, even with a less powerful warp drive.
So even a baby warp drive, something that maybe can't get us to Alpha Centauri just yet, that could completely revolutionize how we travel through space. Imagine zipping over to a space station at L1, that sweet spot for telescopes and stuff. Quicker trips for astronauts, faster response times. It'd be a game changer. But how do we go from all this amazing theory to actually building a warp drive? How do scientists even begin to test this stuff?
Well, they're working on some pretty mind-blowing experiments. One idea that's really out there is the warp field interferometer.
A warp field interferometer. Okay, now that sounds like something straight out of Star Trek's engine room. What is it, and what could it tell us about warp drive? Okay, warp field interferometer, I'm picturing like lasers and mirrors, maybe even like a bit of time travel thrown in there. Am I close?
You're getting warmer. It's a really cool concept, actually. It builds on this other experiment, the Michelson-Morley interferometer, you know the one?
Yeah.
It basically proved that this luminiferous ether thing didn't exist. Big moment in physics.
Right. It's like trying to measure something that's like not even there, trying to catch a whisper. So what are they hoping to catch with this warp field interferometer?
They're looking for these tiny disturbances in space-time, the kind of ripples that, in theory, our warp bubble would create. It's kind of like we can't see black holes directly, but we know they're there because of how they warp light and stuff, right? This interferometer is designed to pick up on those telltale signs, but for a warp field.
Okay, yeah, that makes sense. But how do you even go about creating a warp field in a lab? That's got to be, like, super tough, right?
Tough, sure, but impossible. Not necessarily. One idea involves using this high-voltage capacitor ring to generate a very specific type of disturbance in space-time. They're trying to make this tiny, super-quick warp bubble, shaped like a donut, weirdly enough.
A donut-shaped warp bubble. Now, that's just cool. But seriously,
Yeah.
even if they managed to make a microscopic warp field, like for a split second, that would be a game changer.
Oh, absolutely. It would be a monumental discovery. Proof that we can actually manipulate space-time like this. Even on a tiny scale, it would get everyone thinking, that's for sure.
I can just imagine the headlines. Scientists create warp bubbles in the lab. But let's not get ahead of ourselves here. We still have to talk about the elephant in the room, this whole negative energy density issue. That's still a pretty big hurdle, right?
Yeah, it's true. For a warp drive to work, to actually warp space-time like this, we need this negative energy density. And right now, we don't even know if it exists.
So are we stuck then? Is that what you're saying?
Yeah.
Because I'm about ready to pack for Alpha Centauri.
Not so fast. Physicists are a clever bunch, and they're looking at all sorts of possibilities. Modified gravity theories, those extra dimensions we talked about, trying to find a workaround for this whole negative energy thing.
So even if our current warp drive models need a bit of an upgrade, the research is still pushing the boundaries of what we know about physics. It could lead to all sorts of other breakthroughs.
Exactly. It's that drive to explore, to figure out the unknown, that pushes science forward. Who knows what we'll discover while we're busy chasing warp drive?
Well, this has been an incredible journey. From mind-bending theories to those wild possibilities, it really makes you think, what if we could actually warp space-time, travel to distant stars? What would that mean for humanity, for our place in the universe? It's a question worth pondering, don't you think? A huge thanks to you for joining us on this deep dive into warp drive, and until next time, keep looking up.